Good morning, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm the host for the session today. Welcome to all. Thank you for joining us for a few minutes out of your day. Before I introduce our guest speakers for the session, we did want to run a couple poll questions. Very much appreciate your participation and feedback. And here's what the poll questions look like. The idea is to basically get in line with where we're going to be presenting our material. So if you would please help us by responding in kind. No obligation, no right or wrong answer. We're just trying to, I guess, exchange some relevance to the topic that we're going to be getting into on the deep end in the material. Here's how folks have weighed in on this. Sorry if that was too easy, but you're right. And then the second question, what have you considered as far as the mitigation alternatives to this particular issue? Again, this is strictly what your experience has brought to the table. All right, looks like we have a consensus here. So here's how people have responded on this question. Thank you for attending. Thank you for participating. So Dwaraka Padimiti is our guest speaker for today, and his experience as a design engineer and lead electrical engineer on large projects in the oil and gas industry. Today, he's the regional business development manager and field applications engineer for ABB's electrification business based in Houston, Texas. We also have joining us Peter Sutherland, who's a senior power systems engineer with ABB in upstate New York. I'd like to hand the podium over to Dwaraka. You now have the podium.
Thank you, Jim. Let me share my screen. Sounds good. Thanks, Jim. Good morning and good afternoon, everyone. And thank you for your time for attending this webinar. Today, I would like to talk about some of the applications of arc flash relays and a unique device called as high-speed grounding switch, or the other name is UFS, or ultra-fast earthing switch, which is an IEC name, right? So I will talk about some of the applications and how we can effectively use these devices for mitigating arc flash hazards in your installations, right? So quick safety topic before we move on to distracted driving is one of my pet peeves. 80% of the people engage in smartphone activities while driving. So everything like social media, news, email, everything is just a click or a swipe away. So pay close attention while you're driving. And every time a phone buzzes while driving, resist the urge in trying to attend to the call or attend to the instant messages, right? So as Jim mentioned, my name is Dwaraka Padimiti. I'm the field application engineer based in Houston, Texas. And we also have Peter Sutherland, who is the senior power systems engineer, part of our EL services group. And he's based in Schenectady, New York. Today's course objectives, I'll start off with identifying some of the potential issues or instances where an arcing event can occur, identify the key parameters in the energy equation, and investigate what parameters we can tweak around with in order to reduce the incident energy levels, differentiate between a passive and an active mitigation technology, talk about some of the pros and cons of both those solutions, and in particular, we are going to talk about the high-speed grounding switch and some of its applications. So we have already run the poll question. So internal arcs, it's very well known in the industry over the past 30, 40 years, maybe 50 years, right? So it could originate due to external factors such as human error or pollution accumulation or dust ingress, just because of the environment where the equipment has been installed. Sometimes animals creep in to the equipment and create arc flash over the different phases, right? So, and in other cases, you can have like bad or loose connections on your cable connections, which can, over the period of time, can lead to a arcing event, right? So, these are some of the factors that could lead to a internal arc within your equipment. A quick overview, right? So when you have an arc flash event, like it actually goes through a high impedance, right? So because the arc flashes over through air, and instantly you have a really, really high temperature of about 20,000 degrees centigrade that is being developed inside your switchgear, that could lead to two different phenomena. One is the rapid pressure rise, and the other one is the melting of the metal of your switchgear and becoming into a ball of fire, right? So those are the two after effects when arcing fault initiates in your equipment, right? So, and both these lead to the release of plasma and hot gases and debris that could, if you have an arc resistant equipment, you can channel them safely through the plenum on top of your switchgear and then run it outside of your PDC building or any house, or in other cases where if it's a non-arc resistant equipment, it could actually lead to a potential life-threatening injuries to the personnel standing in front of the equipment during such an event. So I have I listed some of the methods that are most popularly used to reduce the incident energy levels, right, during an arc flash event. So one of them is very popularly known as zone selective interlocking, differential relaying, which is also well known, and the other one is a reduced energy maintenance switch, right? So we call it as a reduced energy let through REL. Is a setting, you know, on all our low voltage breakers, whether it's AVB, Emax2 breakers, or the legacy GE low voltage breakers, right? So it comes with a local indication where when you have an operator standing in front of an equipment, you can activate that reduced energy let through switch, and it switches over to a second instantaneous. We call it as 2I, and when the 2I second instantaneous is activated, you have a really fast clearing time of about 30 milliseconds, which is roughly 2 cycles, when there is an arc flash event that occurs, right? So the incident energy level is significantly reduced to about less than about 2.2 calories per centimeter square, which is categorized as HRC category 1, right? So this is the second instantaneous is a inherent feature of our low voltage breakers, as I mentioned, right? It's a very popular device or an option to use, right? So so let's look at some of the other methods that are popularly used. We categorize them into two different mitigation technologies, arc mitigation technologies. One is called as passive arc mitigation, and the other one is an active arc mitigation, right? So when we call it as a passive, we are not really clearing the or stopping the arcing fault from occurring. So we are using like, for example, like chambers or plenum to safely exhaust any kind of debris that could form due to an arcing flash within your equipment, and safely route them outside of your e-house or a PDC building, right? So, and the other one is a remote tracking device, which is also very popularly known and utilized right? So and the other solution is a light detection relay. So for all these solutions, you have an arcing fault that occurs within your equipment and lingers over for at least 80 to 100 milliseconds, right? So it's a really critical parameter to keep in mind when we are designing our equipment, whether to choose a passive arc mitigation or an active arc mitigation. So on the other hand, we have an active arc mitigation technology where some of the examples are fault current limiters or ultra fast earthing switch, as I mentioned, or the high speed grounding switch, which has a name as arc limiter as a trade name, right? So using the active arc mitigation technologies, we are actually eliminating the arcing event within less than 5 milliseconds. So comparing the 5 milliseconds to 80 to 100 milliseconds, it's a significant difference where you can actually, in addition to protecting your personnel, you can also protect the equipment. So your downtime, if an arcing fault occurs, significantly reduces. You do not have to replace any of the vertical sections. Like for example, in an arc resistant switchgear, if you have an arcing fault, you are protecting the personnel for a type 2B like AFLR, right? So, but you are damaging your equipment where you may have to replace one or two sections of your switchgear, whether it's medium voltage or low voltage. That is clearly defined right here, right? So you can use a 0 PPE or a class 1 HRC rated 1 PPE as long as the breaker doors are closed for an arc resistant equipment, and none of the personnel will be affected, right? But you do not limit the amount of incident energy level that is occurring inside the equipment, right? So on the front, definitely you have a category 1. There is no category 0 now, right? So it's a category 1 PPE, right, for an arc resistant equipment, but there is some significant damage within your equipment for an arc resistant switchgear. Similarly, for a remote tracking device, it's very well known, like where the arc blast expands volumetrically, right? So the farther away the operator is from the equipment, the safer it is for them to operate the equipment, whether it's tracking in or tracking out a breaker. But on the other side, some of the disadvantages include you're not really reducing the available incident energy levels. Rather, you are putting the operator outside of the zone of blast, right? So you are definitely protecting your personnel, but there is some significant damage that could occur within your equipment. So this is actually an older equation from IEEE 1584 2002. It would be similar even in the 2018 edition. I would think, like if looking at the instant energy level equation, right? So there are two parameters that we can play with. One is the time, and the other one is the distance. So the larger the distance, the lower is the incident energy level, and which is what we are doing with the remote tracking device, where we plug in that remote tracking device, and then we bring the operator like 20 feet, 15, 20 feet away from the equipment. So by increasing the distance, the operator is not exposed to a higher incident energy level, right? And the other parameter that we can play with is time, right? So if we can reduce the time significantly, we can directly, proportionally reduce the incident energy level that is being generated in front of the equipment, as well as within the equipment. So one of the other passive arc mitigation solutions is using a light detection relay, right? So one of the advantages is it's a very, very fast acting device that is exclusively used for an arc flash incident in your equipment, right? So you can use two parameters, right? So one of them is the light sensing, and the light sensing is a differentiator because when you have an arc flash in your equipment, it creates a light intensity that is 5,000 times brighter than the natural light, right? So it can be easily differentiated between an arc flash incident as well as compared to just an exposure to an outdoor environment, right? So in conjunction with this light sensing, we also add another function, which is an AND function, right? So when we put in the current sensing, instantaneous current sensing, so we do not risk any kind of nuisance tripping, right? So if you use a REA 101, which is an arc flash relay, with these two parameters, we are definitely going to be 100% sure that you have an arc flash incident that is developing within your equipment, and within less than 2 milliseconds, the REA relay or an arc flash relay can send a trip signal to your main incoming breaker. So there are two high-speed output contacts on the relay that can be configured to, if you have a main-to-main, you can trip one main incomer, as well as you can use the other high-speed output contact to trip your tiebreaker, right? But one thing to keep in mind is is the breaker operating time, right? So if it's a medium voltage switchgear, and if you have typically like a 3-cycle or a 5-cycle breaker, considering a 5-cycle breaker for the worst case scenario, it could be anywhere from 75 to 80 milliseconds until you completely interrupt an arc flash event within your equipment, right? So there is a possibility of an arc flash that keeps developing within your equipment for about 80 milliseconds. So here is a nice picture that shows, right? So as the time progresses, the amount of energy that is being developed inside the switchgear keeps rising exponentially. Right around 100 milliseconds is where your cable starts catching fire, and in about 150 milliseconds, the copper bus bars start catching fire, right? So you have typically less than 100 milliseconds if we have to minimize the damage within your equipment. So this is another comparison with using an REA relay with a 3-cycle breaker, where you have about 50 milliseconds of reaction time compared to a time over current relay with a 3-cycle breaker. When it is clearing a arcing fault, it could take up to like 150 milliseconds. Comparing that with a 5-cycle breaker, where it could take up to 80 milliseconds using an REA relay, which is an arc flash relay. And if it's a time over current, we are well over the 120, 150, close to like 200 milliseconds, at which point you have already done significant damage within your equipment. So these are some of the examples on how we do the fiber routing within the medium voltage switchgear. The red signifies the fiber optic cable going through the breakers, and the violet is going through the transformers, the voltage and bus and bus PT and line PT, and the green is the cable going through your cable compartment, and then you have the blue that is going through your main bus compartment. So it's kind of shows right here on the cross-sectional view. So we have the green area, we have the red, we have the blue, as well as the violet. So here is another depiction of you doing a fiber optic routing through the two high medium voltage switchgear when you have two breakers, right? So we can create a loop within each of that vertical section, where we can route the fiber optic cable through the breaker compartment all the way through covering the main bus compartment, the cable connection compartment, and then going back into the breaker compartment of the bottom breaker, right? So I mentioned about a couple of active arc mitigation technologies, right? So one of them is a fault current limiter, and the other one is the ultra fast earthing switch. So for this particular presentation, I'm going to talk specifically about the UFS, but the presentation slides that you guys received should talk about briefly about fault current limiters as well, right? So here I'm going to talk about a unique principle where we are going to eliminate an arcing fault in less than 4.5 milliseconds, right? So for this, we use the arc flash relay as the initiating element, right? So when there is an arc flash within your equipment, like within 2 milliseconds, the arc flash relay is going to detect the fault, and it's going to send a trip signal to the electronics of the UFS, of the ultra fast earthing switch, which in turn puts a three-phase to ground fault on the bus, so that in about another 1.5 milliseconds, you are converting that arc flash incident in your equipment into a three-phase bolted fault, which can be withstand, which typically the equipment can withstand for about 2 milliseconds, right? So with in about 4.5 milliseconds, you are converting that arc flash incident into a bolted fault, whereby the incident energy that is being developed inside your switchgear is limited to less than 1.2 calories per centimeter square, which is effectively like a category 1 high HRC, right? And so that's the key differentiation of this equipment, where it does not let the arc flash develop within your switchgear beyond 4 to 5 milliseconds. So you have a conventional fault where you have a typically like a low impedance, right? So whereas if you have an arcing fault, it is between air, and then it can be explosive and can cause significant damage to the equipment as well as to the operator, depending upon the type of the equipment, right? So we are converting this kind of a fault into a conventional three-phase to ground fault, which creates a low impedance path for the fault, and that can be effectively interrupted by your 5051 by your relay, and can interrupt or eliminate or isolate this conventional fault in a safe manner, right? So here is a specific application where you have a fused switch that is connected, that is feeding a oil or a distribution class transformer that is directly connected on the secondary side to a low voltage equipment, which in this case it could be a low voltage MCC or a low voltage switchgear, right? So typically you have like a 2 MVA or a 2.5 MVA distribution transformer, and on the upstream side you have a fused switch, fused disconnect, and on the downstream side you have a low voltage equipment. And in these kind of typical installations, if you have an arcing fault on the low voltage side, because the arcing fault only creates a magnitude roughly around 30% of a three-phase voltage fault, the fuse takes longer time to clear the fault, and sometimes the fuse doesn't even clear such kind of an arcing fault, in which case you have a really high incident energy level on the low voltage side of the transformer. Sometimes it could be about 50, 60, or 90 calories per centimeter square in such applications, right? So in that particular scenario, when we install an arc flash relay with a high speed grounding switch or a UFS on the primary side of the transformer, in that kind of a scenario, if you have an arcing fault on the low voltage equipment, the arc flash relay in conjunction with the high speed grounding switch will eliminate or transform that arcing fault on the low voltage equipment to a bolted fault, three-phase bolted fault on the primary side of the transformer, which will be cleared by your upstream fuse in 1 to 2 milliseconds. Because of this three-phase to ground bolted fault, the clearing time of your E-rated fuse is really fast, and it's going to melt much faster and much quicker. And we have actually performed a KEMA testing for this particular setup, and we were able to measure the incident energy to be like less than 1 calorie per centimeter square on the low voltage side of the equipment. And yeah, so the fault has been cleared. That fault has been cleared in less than 4 milliseconds in that this particular scenario. So the UFS element itself, we call it as a primary switching element, and this is the cutout of one of the elements. So we have 3 elements connected. On the top side is connected to each of the phases, and on the bottom side is connected to the ground bus. And we have like a charge. Think about like a airbag in your car, right? So it has a discharge element. Once it gets a signal from the QRU 100, which is the electronics or an electronic tripping relay for the UFS, the discharge, the microgas generator discharges in less than half a millisecond, and in about another half millisecond, half to 1 millisecond, this particular connection gets connected to the top of the element, thereby grounding your bus bars to the ground, right? So this whole operation takes about 2 to 2.5 milliseconds once it gets a signal from the REA relay. So it is a typical setup where you have your REA relay, and you have your fiber optic loop running through your low voltage switchgear that is looking for a potential arc within your lineup. And once you have a fault detected, arc fault detected, the REA 101 has a reaction time of less than 2 milliseconds that sends a signal to the QRU, which we call it as a quick release unit, or the electronics controlling the UFS element, right? So it takes another 0.4 milliseconds to send the trip signal to these primary switching elements, right? So it takes then the UFS elements take about 1.5 milliseconds to connect the bus bars to the ground, right? So in total, about 4.5 milliseconds, you are converting this arc flash incident into a bolted fault by creating a low impedance path, so that your upstream fuse or a breaker can operate and isolate this bolted fault within your system. So here is another sequence of events, right? So when you have an arcing fault on your switchgear, you have a CT that looks for the current and the light by the arc flash relay, and in conjunction of these two, it's going to send a tripping signal to the tripping unit that in turn puts a bolted fault on your system. And as a standard, we can actually also send a trip signal to your upstream breaker. So before your 5051 actually on the breaker reacts for any kind of fault, in about 4 milliseconds, you are actually sending a trip signal to your breaker to open. So in about depending upon whether it's a low voltage equipment or medium voltage equipment, we can quickly isolate this 3-phase to ground fault by the upstream breaker. So here is a similar curve that I showed in the previous few slides. So for an arc flash relay, we are somewhere in the range of 80 to 100 milliseconds. And for a conventional protected device, especially for an arc flash event, we are in a highly explosive range where you could have like some heavy injuries to the personnel as well as to the equipment. And here is the reaction time by using a UFS or a high-speed grounding switch, where you are completely eliminating an arcing fault in about 4 to 5 milliseconds right here. So here is a reiteration of what the elements is. So this is how the elements are going to look like, and it's a very compact device, and we need one per phase, right? So it can be a solution for a new switchgear, for a new uh, uh, either non-arc or arc resistant switchgear, or it can also be installed as a retrofit application, right? So and so one of the things to keep in mind is it would create a three-phase to ground voltage fault on your bus, right? So that needs to be evaluated whether the system can withstand your existing system should be able to withstand for about 2 seconds. So that should typically not be a problem. So this particular equipment is a medium voltage rated up to 40.5 kV, but it can also be used for low voltage applications as well. For about low voltage applications, it is rated up to 100 kA, and for medium voltage applications, it is rated for up to 63 kA for 1 second and 50 kA for about 3 seconds. So it's a pretty robust device that can be used for either for low voltage or for medium voltage applications. So some of the typical applications, right? So as I showed on the previous slide, so this is your low voltage equipment. You have your fiber optics running through your low voltage equipment connected to an REA relay, and it has a CT input coming in from the primary side of the incoming breaker. And when the REA relay reacts, it's going to send a trip signal to the upstream breaker, as well as going to send a trip signal to the QRU100 that puts a voltage for that sends a signal to the UFS and kind of eliminates this arcing fault into a three-phase to ground voltage fault. Similarly, for a main equipment, it's a similar setup where you have your REA system and the UFS system dedicated for each side for bus A and bus B, and it's the exact same configuration. And the REA system on bus A and bus B are going to communicate with each other, and depending upon if you have a arcing fault on bus A side or on bus B side, right? So if there is an arcing fault on this bus bar 1, the REA is going to send a signal to the REA system on bus bar 2, so that it's not going to trip your main breaker on B side, and whereas the system 1 is going to trip the main incoming breaker as well as your tie breaker. So it's going to isolate this particular section when you have an arcing fault somewhere in this particular equipment on the bus bar 1 side. So for this particular setup where you have a fused switch connected to a distribution class transformer with low voltage equipment on the downstream side, so we have actually performed a KEMA testing, and these are some of the pictures, and let me show you guys. So this is the KEMA setup for the low voltage equipment, where you can see the wire that is run across the phases in order to simulate a arcing fault, and then you have a point sensor that is looking for the light, right? So this is a part of the arc flash relay. And the video on the left was so it's actually we did a test by using a conventional relay where the equipment just blew up, right? It's becoming like a ball of fire. Whereas on the right side, as you can see here, in less than 4 milliseconds, all you see is a little bit of a soot coming out of the equipment, and that's what we see on the pictures, right? On the right side, we have a little bit of soot in your breaker compartment that you can clean up, and as you can see, very minimal or to no damage within your equipment, where you can put it back in service much faster compared to the significant damage it caused on the first picture, where you may have to completely replace this particular breaker section, right? And these are the curves that we were able to monitor from the schema test, right? So it took about 2.23 milliseconds for the trigger wire to melt and send a arc flash to trigger an arc flash element, right? So and within that time, you're actually going to put a bolt. It takes another 1.5 milliseconds for the arc flash relay to operate and send a trip signal to the high-speed grounding switch. And from this point, if you look, the current starts dropping, right? So because the voltage has completely gone down to zero, right? So this point is the voltage on the system is limiting to zero, right? So and in about 1.1 milliseconds, primary current limiting fuse starts melting and it clears in about another 1.3 milliseconds. So in a total of about 3.8 milliseconds, 3.9 milliseconds, so in about 4 milliseconds from the time the arc flash has been detected, we have cleared completely the arcing fault, as well as cleared by the upstream fuse that clears in about 1.3 milliseconds, right? In total, about 6 milliseconds from the time an arc flash has initiated in your equipment, you have completely eliminated and isolated any kind of fault in your system. Some of the typical installations, right? So this is actually a retrofit installation where we have installed a UFS with the CTs for the REA, CT input for the REA, and it's a similar picture on the other one. And I would like to wrap it up with showing the arc limiter being integrated in our low voltage switchgear, right? So here we show a withdrawable unit that can be integrated in our low voltage MNS switchgear. So that's a unique feature where for a non-arc resistant equipment, we can integrate the UFS elements within the switchgear itself, right? So for the main time and we can connect it in such a way. So this particular concludes the presentation, and kind of I went through all the bullet items, right? So talked about differences between different types of active and passive mitigation technologies, talks about some of the pros and cons, identified some of the solutions and some of the arc mitigation solutions. And now we would like to I would like to highlight how we model this EasyPower, this particular device in EasyPower. So as you can see here, I have a few screenshots that will be shown by Peter on how we can model this in EasyPower and show the differences using the UFS and using with the UFS and without the UFS.
All right, Peter, are you ready? You now have the podium.
I'm ready. Show my screen. Okay. What do you see?
Yeah. Now we see the PDF as well as your EasyPower, Peter.
Excellent. Okay. The one on the left is the one-line diagram of the system, similar to what was just discussed. There's a low voltage switchgear here. This is a retrofit, so it's an older unit fed by a 1000 kVA pad-mounted transformer, which is fed by a 12 kV overhead line. And I have modeled that in EasyPower. Let me just make it a little bit bigger here. So we'll see there's a utility source at 12 kV coming down through a substation that you don't see out there, the line. Then there is the pole top fuse link, 65 amps, and then there is a bayonet current limiting fuse installed in the pad mount transformer itself. And then on the secondary of the transformer, we have a cable that takes us to the low voltage switchgear, and the main breaker is what we're focusing on here. So if we look at it now in the database model, what we have is just a automatically calculated time current curve, and we're going to look at both including and excluding main arc flash. So we go here, and what we see is on the bus itself, we get 1.5 calories. That's limited by the main breaker. And then on the line side of the main breaker here, we're going to get 53 calories, which is higher than you want to be exposed to, shall we say. So what we're going to do is putting the UFIS on the primary of the transformer up here. We're going to impose a bolted fault on the circuit within less than 5 milliseconds, and that will bring down your sorry, it will, that's not what I want to do. That will bring down your incident energy. To do this, we go back into the database version and go to user-defined times. We're going to put in a UFIS, and it's going to be a relay function 50, and it will be 0.005 seconds. Whoops, 0.005. That's 5 milliseconds. Now, you saw it was about 4 milliseconds, but we're being a little bit on the safe side here and calling it 5. Then we go to short circuit again and fault it, and you'll see we get 0.2 calories on both the 480 volt bus and on the line side of the main breaker. And once this happens, now what we don't see is that your primary fuses are going to blow, and so your transformer will be de-energized right away. And one advantage of doing this, putting your UFIS on the primary side, is your transformer doesn't really get exposed to the short circuit current of the bolted fault. It only has the limited arcing fault current. So it's probably better for your transformer to do it this way. If you can do it, if you have the proper switching up above, so you're not shutting down your medium voltage system. So that's what I have. Are there any questions? Anybody like to?
Yeah, so I'm looking at the questions, Peter, and
Yeah.
just the way the Dwaraka did it, many of the questions were answered in turn as they came up. So let me just kind of review a couple of these, and if they were part of the presentation, we can just skip over them. So a first question from Rolando: isn't light detection relay considered active arc mitigation? We had a couple of people thinking that using an arc sensing relay would be considered active mitigation. Do you have an opinion on that?
So like I mentioned, right? So in an active, if it's an active arc mitigation solution, you are actually eliminating an arcing fault, right? So even though your light sensing relay is a fast acting relay that can detect an arc flash in about 2 milliseconds, you still have that operating time of the breaker, depending upon if it's a low voltage or a medium voltage breaker. It could be anywhere from 50 to 80 milliseconds, right? So up until your breaker is interrupted, right? So you still have that arcing fault that is developing within your switchgear for about 80 milliseconds. So that's the basic difference when we classify a passive arc mitigation solution to an active arc mitigation solution. So in an active arc mitigation solution, you do not have an arc being developed for beyond 4 to 5 milliseconds. So that's how we differentiate the different solutions.
Yeah. The next question from Rolando: for a typical installation, what's the impact of having the UFIS in terms of size of the cubicle or bucket? How much bigger would it be compared to installation without it?
I'm sorry, I missed the first part, Jim. for a retrofit?
For a typical installation.
Oh, for a typical, okay. So I showed a couple of pictures, right? So it's a very compact device, and if it's a retrofit solution, it can be installed in the incoming cable section of your main breaker, and we can run the cables back to the low voltage unit, right? So we need some space to install the REA relay as well as the QRU unit within your low voltage compartment of the incoming breaker, whether it's a low voltage or medium voltage system, right? So, but we have done quite a few retrofit applications and installations. So our services team can do like a site survey and figure out if there are any empty cubicles that we can use to install those equipment. But as you have seen in those pictures, the device itself will look very similar to like a surge arrestor. It's a very, very compact and small device that can be installed in a limited space.
So here's a question from James. He says specifically, any thoughts or recommendations or experience using arc detection relays for a motor? Specifically, they have a 4160 volt, 2500 horsepower slip ring motor that has had a couple of arc flash events in the brush box, and it's been proposed to install an arc flash detection system in the brush box. Would you recommend this application or any alternative solution?
It's an interesting question. I believe in a slip ring motor, like you are going to have arcing event pretty much all the time, right? Something that we may have to think about, like on how we can implement it, because you would have that arcing event occurring every time the motor rotates, right? So I'm not really sure. We may have to
we can
check
follow
with
up.
our motor group.
That's right.
Yeah, we can definitely follow up, and I can talk to some of our motor group and get some thoughts from their end.
Okay. Lexman says for an HRG system, the application guide says it must prevent this ground nuisance alarm, or the MV switch would be installed or retrofitted with a shunt trip activated by one of the QRU's trip out contacts. The question is, I've been able to find shunt trips for the 5 kV e-fuse. How would you apply this to a 5 kV HRG system with fuses so as not to trip the grounds?
We have an application guide that pretty much showcases all different scenarios. I can probably share it with you, Jim, and then you can send it to all the audience.
Okay.
But that should answer the question. That actually shows different pictures on how we implement the UFS solution for different types of grounding systems, whether it's medium HRG or LRG, right? So or if it's a solidly grounded system, right? So I'll share that with you, Jim, and then you can send it over to all the audience.
Howard's question is, does the available fault current in the system get reduced when the UFS is installed?
Not really. So the UFS is only a arc flash mitigation solution. So it does not change the rating of your equipment in any way or any sense. So even though it has it creates only 1.2 calories per centimeter square, you cannot certify a non-arc resistant switchgear with UFS installed as equivalent to an arc resistant switchgear. You cannot label it that way, but it definitely adds value in limiting the damage to your equipment, right? But to answer your question, it does not change any of the ratings.
The next question is the grounding equipment reusable, or does it need to be replaced after the fault?
Yeah, these are typically one-shot devices, but we recommend having 3 spares, and that's the reason why once it operates, you can switch them over to your spares, and you can send the activated devices back to our factory in Ratingen, Germany. We will refurbish them and send it back as your spares. So for a primary solution, we recommend having 3 spares. and once it activates, you can quickly replace them by unbolting on the top of the equipment. And these devices doesn't show any kind of external damage, right? So once it operates, it's just going to put a bolted fault, and then that's quickly eliminated by your upstream device, right? Protected device.
Mm-hmm.
So yeah, we recommend having 3 spares for the installations.
So I think that's the end of our list of questions. Just for the audience sake, we will be posting the PDF version of your presentation when we post the video. Thank you for a good presentation, both Peter and Dwaraka. Appreciated your contribution, and we look forward to working with you down the road.
Thanks for hosting us, Jim, and thank you to everyone for attending this webinar.
Thank you.
Have a good day.